Magnetostatics, devices. We'll start this lecture with some preliminary concepts, talk about things like inductance, flux linkage. Then we will talk about energy in the magnetic field. Given all of this background, we'll lay out a recipe for analyzing inductors. So we'll be able to hand you this twisted piece of metal, and you can work through it and calculate the inductance of that twisted piece of metal. So to demonstrate that recipe, we'll work through 4 different examples. And that'll be it for this lecture. Preliminary concepts. We have this concept for magnetic flux linkage, and I think a lot of textbooks do a poor job of explaining this. It's a simple concept, but I think tends to come across rather confusing. So let's just start off with magnetic flux. In the diagram here, we're showing a wire that forms a single loop. And if we inject a current into this wire, that will of course create this magnetic field through the center of that. And we can calculate the flux. If we define this area in the cross section of the loop, we can integrate the magnetic field that is punching straight through that. And if we add all of that up, we integrate it, we get the magnetic flux. So this current I has produced a flux B. Now we have to ask the question, what if we use multiple turns? We have essentially the same cross-sectional area, but if we inject the same current, but there's multiple loops, each of those loops creates its own B field. And in fact, we end up with a much more intense B field just because there's more turns. And so if n is the number of turns, our resulting B field is n times the original B that we had for a single turn. Well, we can still integrate in the cross-section and get the flux. However, to account for the number of turns, we can write our original flux equation and multiply that by n. So magnetic flux linkage is really the same thing as magnetic flux, but it accounts for having multiple turns. So the flux linkage, which is the symbol lambda, is the number of turns times the magnetic flux for a single loop. And this lambda is not wavelength, not even related to wavelength, because we're talking about magnetostatics here. It's just an unfortunate reuse of the symbol. We haven't even used that for wavelength yet. That comes later in the course. So that is the concept of flux linkage. Now we talk about inductance. So it turns out the magnetic flux linkage is proportional to current, and that makes sense. We put a current into the wire, it creates a magnetic flux. We account for the number of turns, and magnetic flux is proportional to current. Well, it turns out inductance is the proportionality constant that makes that equation exact. So our flux linkage is the inductance times the current. So if we solve this for the inductance, that is the flux linkage divided by the current. So we have an equation to figure out what inductance is. And if we stare at this long enough and think about this long enough and use what we know from circuit theory, the inductance is really a measure of how well the device stores magnetic energy. If it has more turns, it's going to have a greater ability to store that magnetic energy, and the inductance will be higher. Now, inductors are a little bit analogous to capacitors. Capacitors store and release electric energy. Inductors store and release magnetic energy. Inductors do this in a way that tries to keep the current flowing through it at a steady, constant rate. And if we try to switch that current, those inductors can generate thousands of volts to try to keep that current flowing at a constant level. So for example, if we have current flowing through a coil and we shut it off really quickly, maybe we open a switch in a circuit, there could be arcing in that circuit if we don't give the inductor a discharge path. So stun guns and things like that, a lot of times will have inductors in them. From circuit theory, we remember that the energy stored in an inductor is 1/2 Li squared. And the energy here is, the units has joules. So we can solve this expression for L. And we essentially have the energy divided by current squared is inductance. Well, in the previous slide, we related inductance, flux linkage, and current. And we can substitute that back in. And now we have an equation for the flux linkage that gives us another way to interpret it. And we really see that the flux linkage is a measure of how well it's storing magnetic energy, how well the inductor is storing magnetic energy for a given amount of current. More windings for a given current, it will have a greater ability to store magnetic energy. So it makes sense that the flux linkage is proportional to number of turns. Now let's talk about energy stored in the magnetic field. We did this for electric fields, but it's actually a very different type of story to figure this out for magnetic fields. So let's get right into this. We're going to arrive at our expressions for the energy in the magnetic field by analyzing this box over to the right. So this is a cube and it has dimensions delta x, delta y, delta z. And eventually we're going to let these go to 0. But right now we're keeping them some finite size. We're going to analyze this box and our equations for the energy in the magnetic field will fall out of this. So the top and bottom of this box, these are conductors and we're going to let them carry a current delta I. It has to be a delta I because the size of the box is a delta x, delta y, and delta z. The first thing we'll do is apply Gauss's law, and so we'll integrate the magnetic field in the cross-section of this box. So we're in the xy plane. So remember our expression for magnetic flux, we'll integrate over that area. We're integrating B dot ds, and since we're integrating over a differential box, really what we get is a differential flux. So our B field is oriented in the y direction, so our expression is just B and then unit vector AY. And in this case, our differential vector surface element, it's in the xz plane, so we have a dx dz, and then the direction of that vector surface is in the y direction. And we needed it really to be in the y direction because we're doing a dot product, and if it weren't that, it would have disappeared. And then our integrations will be going from 0 to delta x and 0 to delta z, just as we're showing here, 0 to delta x and 0 to delta z. So that covers that whole surface. So the b is a constant. It can come to the outside. Our dot product, ay dot dy, that just gives us 1, and we're only left with dx and dz. That's a real simple integral to perform. We just end up with delta x times delta z. That is the area of that cross section times b. That equals our delta flux, delta psi. Second thing we'll do is we'll apply Ampere's circuit law around the bottom conductor. So we'll integrate from A to B, B to C, and C to D, then back D to A. So it's a closed contour line integration. So our general equation is a line integral of H dot dl. And we'll get a delta I because this is a differential delta box, if you will. So we're doing our single line integral, and it is a closed line integral from A to B, B to C, C to D, and D to A. So we write that as 4 different line integrals. And we'll look at each one of these individually. Well, right away, we can see that the magnetic field is in the y direction. So when we're integrating in the z direction, there is no component of the magnetic field in the z direction. So those 2 line integrals become 0, and we don't even really have to deal with them. We have 2 other line integrals. We have from A to B, and then we also have from C to D. Now from A to B, there's a magnetic field between those plates, but there's a magnetic field due to both plates in that area between the plates. So that's why we have a 2H. The magnetic field is sort of twice the intensity that we would get from a single plate, but since we're seeing the magnetic field from 2 plates, it's a 2H. And that explains why when we're integrating from C to D, there's only 1H. There's also a negative sign here because we're integrating in the negative Y direction. So if we perform these integrations, we end up with a 2H minus an H, and we're just left with an H, and then a delta Y. Why the delta Y? Because that is the length of this line for our line integrals. Okay, now back to one of our original definitions for inductance. Our inductance was the flux divided by current, but now we have a delta flux and a delta I and a delta L. And let's think for a second, why aren't we using flux linkage here? Because that's the more general concept. Well, we don't have multiple turns, so we just use the ordinary flux. Well, we have expressions for these. We derived our flux as B times delta X delta Z, and we just derived our delta current as H times delta Y. Now we can recognize that we have a B divided by H. That's just the permeability of the medium. So in fact, our inductance is permeability times delta X delta Z over delta Y. Back to our equation for circuit theory, the energy stored in an inductor is 1/2 Li squared. So we have a delta L and a delta I, so this will give us a delta energy. Let's go ahead and plug in our expressions for everything. We have our expression for delta L here we just derived. We'll plug that in for delta L. And our delta I is just H times delta Y that we've plugged in here and then also squared. And we end up with 1/2 mu H squared delta X delta Y delta Z. Our delta X, delta Y, delta Z, those are the three linear dimensions or the sides of our cube. Multiplied together, that is the volume of our cube that we'll just write now as delta V. And this expression already should be starting to look familiar from our discussion of electrostatics. At this point, we're going to let the volume of this box go to 0. So the actual energy density in the magnetic field is our delta W divided by the volume. That gives us our density, but then we're also letting that volume go to 0. Well, we had an expression for our delta Wm, and we divide it by delta V. These delta V's cancel, and we have an expression for the energy density of the magnetic field. It's 1/2 mu H squared. And if you remember from electrostatics, we had an energy density in the electric fields as 1/2 epsilon E squared. So the same thing has happened here. We had to arrive at it in a different way, but the conclusion was the same. So if we have this energy density, anytime we have a density term, there's an integral hiding behind it so that we can add it up and get the overall energy in this case. So we integrate the energy density to get the overall total energy stored in the inductor. And of course we have this handy expression to put in. We had 1/2 mu times H squared. So we bring the 1/2 to the outside and we just end up with mu H squared inside our volume integral. So recall we had this expression from electrostatics. The total energy in the electric field was an integral of d dot E. It was an integral of 1/2 d dot E. And this was the general case for anisotropic, nonlinear, whatever sort of media. But most textbooks express the equation this way. And that's for linear, homogeneous, isotropic media. So realizing that the same thing is happening here with the magnetic fields, it lets us write this equation for magnetic fields. And so, in fact, we arrive at two equations. So the general case, the total energy in the magnetic field is the integral of 1/2 B dot H. And that's valid in anisotropic media, nonlinear media, or really whatever. In linear homogeneous isotropic media, that simplifies down to this, and we really just derived this one. And that's the one, if you Google energy density and magnetic field or look in your textbook, that's the equation they give you, but it's really only valid for LHI media. Now let's move on to a recipe for analyzing and calculating inductance of metallic structures. And you'll see this mirrors a lot of how we analyzed capacitance of structures. So step one, we'll choose a suitable coordinate system, and we look at the shape of our device. If it looks blocky and rectangularish, we'll probably choose Cartesian coordinates. If it looks like a cylinder, we'll choose cylindrical coordinates. If it looks like a sphere, we'll choose spherical coordinates. So we choose a coordinate system. At that point, we're going to let the inductor carry a current I0. When we're analyzing capacitors, we let the plates carry a charge Q. This is the analogous step for inductors. So we assume a current flowing through the inductor. At that point, we use everything we know about magnetic fields around currents to calculate the magnetic field intensity around the inductor. So if we have a configuration of metals that makes it very easy for us to know the orientation and the geometry of the magnetic field, symmetry exists, we can just use Ampere's circuit law to calculate the magnetic field. If not, then we have to go back really to the Biot-Savart law to figure out what the magnetic field is. And there we have the line current, surface current, and volume current. But hopefully we've learned enough about fields around currents. We have magnetic fields around line currents and magnetic fields around sheet currents. Those are the most common. Hopefully we can use that so that we can just apply Ampere's circuit law to figure out what the magnetic field is around that current that we've assumed. Okay, so we chose a coordinate system. We assumed a current. We then determined the magnetic field that that current induces. Once we know H, it's real easy to calculate B, mu times H. Now we're accounting for the permeability of the medium. At this point, we want to calculate the magnetic flux because that's in the definition of inductance. So we integrate the flux over the surface and we get flux. And then the very last step is to calculate our inductance. So we have number of turns times the flux. Remember, that's actually flux linkage, but I'm leaving the n explicit here, divided by the current that we assumed. So this should end up being a function of that current I0, and then that should cancel with this I0. And in the end, the inductance should not be a function of that current. That should somehow cancel out of the equation, and that serves as a really good check. There's an alternate way to do that. We can go step 1, 2, 3. So at the end of step 3, we know the magnetic field intensity. We can do something else at this point. Given H, we can calculate the total magnetic energy. If we know the energy, then we just use our circuit theory equation, which knows the energy in an inductor is 1/2 Li squared. We can solve this for inductance. So given total energy, we can divide by the square of the current to get inductance. Both work, both are equivalent, and in the following examples, we'll end up doing both just to illustrate both. Example number 1, a solenoid. This is the classic example of how to analyze a structure to derive its inductance. We start our derivation just with a description of the geometry here. So here's a solenoid, and it's a bunch of wires wrapped around some kind of core that has a permeability mu. The radius of this core, or the solenoid, is A, and then the cross-sectional area we'll call S, which of course would then be pi A squared. Our solenoid will be some length that we'll call L. And of course, we have some number of turns, and there could be a lot of turns, and the turns could be overlapping. We could have hundreds and thousands of turns. So at the end of this derivation, we will derive the inductance for the solenoid, which is this equation. That is our final answer, and the units are in henries. And the rest of this example will be deriving that equation. And this is not an easy one. but it is a great example of how we can apply all of these magnetostatic principles we've learned to calculate inductance. So let's go ahead and dive right into this. Step 1, choose a coordinate system. Well, our solenoid looks rather cylindrical, so I think cylindrical coordinates seems appropriate. We'll let the z-axis run through the center of our solenoid. And then we have this distance rho, that'll be in the radius direction of the solenoid. And then we have our angle phi, which is the angle off of the x-axis. So this is the coordinate system that we will analyze our solenoid. Step 2, we let the inductor carry a current I. Well, there it is. We have current I naught coming in and current I naught coming out. And of course, anywhere along here is current I naught. Well, that was really easy. The other steps aren't quite as easy. This is the hardest step. And once we're finished this, we've essentially solved the problem. It's just a few simple steps away. So this is difficult because we have a long solenoid, lots of turns, and an easy way through this is to calculate the magnetic field due to a single loop. And then we can treat that single loop as sort of a differential slice through the solenoid that we can then integrate through the solenoid to get the total magnetic field due to the entire solenoid. So right now, forget about the solenoid and let's just think about a single loop. So we've placed a single loop centered around the z-axis, and we're observing it, the magnetic field, somewhere up here on the z-axis. So what is the magnetic field at that observation point along the z-axis? Well, to figure this out, we go to the Biot-Savart law for line currents. Our observation point is on the axis. And this gives us an expression for the differential magnetic field at our observation point due to a differential current element. So of course, if we integrate that differential current element around the length of the loop, we'll get the total magnetic field at the observation point. So that is our strategy. So what are the terms in this equation? Our dl in this case is in the phi direction. See how it's rotating around the z-axis? So we have an a d phi a rho. That's our differential length in cylindrical coordinates. What is r? Well, in terms of the rho direction, remember the radius is a. So from here to here, we have a negative a in the rho direction. And then in the z-axis, we're going from the origin out to our observation point. That's a length z, so it's just z in the z direction. That's our vector r connecting our differential current element to our observation point. The cross product. We have a cross product of dl and r. So we plug in our expression for L and our expression for r. Now our r vector is the product of two terms, and we can distribute this cross product so that we essentially have an a phi cross product with a rho, and then the second term which has an a phi cross product with a z. Then that's easier to think through, and a phi cross a rho, that's a negative az, so we have an az here, and then the negative cancel with this negative and we have a positive. And then an a phi cross az, that's a positive a rho. So now we have dl cross r. We still need our r cubed. Well, there's our expression for r. And so the magnitude cubed is simply a squared plus z squared to the 3/2 power. And this is something we've done before too, so we don't need to talk too much about that. We are now ready to go back to the Biot-Savart law and plug in all of these expressions to get a big ugly expression for our differential magnetic field. Now I'm using the subscript 1 here to remind us that this is not the total magnetic field for the solenoid. This is just due to one turn. So that's what the 1 is indicating. All right, we plug in everything we have, and that is our expression for the differential magnetic field. This is the expression that we have to integrate around our loop. So since we're integrating in the phi direction, our limits will be from 0 to 2 pi. That's going all the way around. And so we're integrating this dH1, and that will give us the total H1. Still using this subscript 1 because this is going to give us the total magnetic field just due to one loop. So we plug in our expression for dH1. We see that in the numerator, there's the sum of two terms, so we can actually split this integral into two integrals. Our first integral has an AZ term, so that'll be the Z component of the magnetic field. This second one has an A rho, so that'll be the rho component of the magnetic field. Now, why would the magnetic field have a rho component? Let's look at this R vector that connects our differential current element to our observation point. If we sort of keep going, we can see that we actually have a component in the rho direction. That's how we're going off of the z-axis. But now in your mind, imagine this differential current element moving its way around the whole loop, and we can see that over here this rho component will eventually rotate all the way around the z-axis, and in fact we'll have just as many positive rho components as negative rho components, and we can say that this integral will go to 0 because of that. Now we could leave that integral there, we could do the math and get 0 in the end, but we can just tell from the symmetry of the problem that that will go to 0 and we can ignore it. So we can just proceed with this one single integral because we know the magnetic field will only have a z component just due to symmetry. So that's where we were on the previous slide. How do we handle this? First thing I like to do is factor out everything that is not a function of phi, which in this case is everything. So we're just left with an integral of 0 to 2 pi over d phi. So in fact, this is just 2 pi. So we have a nice expression for the total magnetic field due to one loop. And we can simplify this a little bit. There's a pi here, there's a 4 and a 4. And so we can write this in a form that's a little bit cleaner. So one more reminder, and I know I keep beating on this, but this is just the magnetic field due to one single loop. It's not yet the total. That's the next step. So we derive this expression for the magnetic field due to a single loop. Now back to the solenoid. We're going to interpret that single loop as a differential slice through our solenoid. And when we interpret it this way, that'll let us integrate that over the length of the solenoid to really arrive at the total magnetic field for the entire solenoid. So we need to convert this expression to something that makes sense as this differential slice through our solenoid. And it turns out this is how we write that. So we'll write it as DHZ. We're dropping the 1 now because this is a differential slice through our solenoid, not anymore just for one loop. The thing we have to add here is this N over L to account for the turn density. We could have turns on top of other turns, and we need to account for that. So we have to add this N over L. But that's our expression for our differential current as one slice through the solenoid. And we will integrate that slice over the length of the solenoid. So our solenoid will go from minus L over 2 to positive L over 2, and we're integrating this differential magnetic field that we calculated. When we do that, we then get the total magnetic field inside of the solenoid. So we plug in our expression for our differential magnetic field, and this is what we're left having to integrate. Well, that's kind of an ugly expression, and this is very reminiscent of how we handled the finite line charge, the finite current, and rather than integrate over z, we converted it to integrating over an angle. So that's exactly what we're doing here. So we have our differential slice through the solenoid, and we have our observation point. So rather than define this in terms of a distance z, we'll define this as an angle theta. So if we look at our observation point and draw our line to the outside of the solenoid, that's our angle theta. So the beginning of the solenoid, measuring the angle off of the z-axis, the beginning of the solenoid is an angle theta 1. The end of the solenoid is an angle theta 2 off of the z-axis. So we're integrating from theta 2 to theta 1 instead of negative L over 2 to positive L over 2. And it turns out, while this seems crazy, it will make the math easier for us. So the question is, we want to convert integrating from z over to theta. What do we do with what's on the inside of that integral? So let's look at that next. We need to convert from z to theta. And so we do this from an observation. We have a triangle here. And so the tangent of this angle, it's the opposite face divided by the adjacent face. Well, the opposite face, remember the radius of our solenoid is A, and this face has a length Z. So the tangent of theta is A divided by Z. Well, we can solve that equation for Z, and we get here. So now there's our equation that relates theta and Z. We also need to relate the differential of theta, dz to d theta. And so we get that by differentiating this equation. Now we've related dz to d theta. We'll do one other thing that's a little bit crazy. We have a 1 over sine squared here, and we can write that as a 1 over sine cubed times the sine theta. And the reason we're doing this is that's going to allow us to cancel some terms later. We can make another observation similar to how we did a tan theta. We can look at the sine of this theta. Sine of theta is the opposite face divided by the hypotenuse. So the opposite face is A, and the hypotenuse is an A squared plus Z squared, square root of that. So that's our sine theta. We can then cube that expression, and we get an A cubed over AZ squared, A squared plus Z squared, all to the 3/2 power. And this is a term that appears in that integral that we wrote that we said was going to be confusing to handle. This will allow us to cancel that. Let's see how that works. Okay. So here's the integral that we had that was over z, and we were converting things term by term. We said we would start our integration at theta 1. We said we'd end the integration at theta 2. Our dz term related to d theta was this. We derived that on a previous slide. And this denominator expression is now a cubed over sine cubed theta. So if we plug all of this in, this is what we end up with. We've eliminated z, and we have angle now. So we're ready to run this integration. Now there's a bunch of signs floating around. We can cancel all that stuff, and we can bring a bunch of constants to the outside, and man has this simplified down. So these are all constants that are not functions of theta, and all we have to do now is integrate sine theta from theta 1 to theta 2. So that's what we're doing here. We integrate from theta 1 to theta 2. We get this answer. And that is very reminiscent of what we got when we did the finite line charge and the finite current element. Now what we'd like to do, rather than have these cosine thetas, let's use the magnetic field, or assume the magnetic field inside the solenoid is the magnetic field of an infinite solenoid. So what is theta 1 and theta 2 for an infinite solenoid? Well, if it's an infinite solenoid, this part of the solenoid would go out to negative infinity, and in fact, theta 1 would come all the way to the z-axis and be 180 degrees. So theta 1 is 180 degrees for an infinite solenoid. This end of the solenoid would go out to positive infinity, and then in fact, theta 2 would then go down to 0 for the infinite solenoid. So we can plug in these two angles into our expression above to get the magnetic field inside of an infinite solenoid. So we plug in those angles, and that's the magnetic field we have for an infinite solenoid. And so it simplifies our problem to let that be the magnetic field, even though we know that's not quite the case, and there's going to be some fringing and stuff near the edges, but this will get us pretty close. Finally, we're ready to go to step 4. We've done the majority of the work and calculated the magnetic field, but we need the magnetic flux density. We get that from the constitutive relation, and we use the same expression we had on the previous slide, but now there's a permeability sitting there. We have B. We need B because step 5 is calculating the flux. So let's go ahead and do that. We found that the magnetic field is in the Z direction. And for the infinite solenoid, we found that it's going to be uniform. It's in the Z direction. And so to calculate the flux, we want to integrate in the cross section of the solenoid. And so that's exactly what we'll do to get the flux. When this happens, since B is only in the Z direction, the B comes to the outside, and we just get, our integral is just left with the integral of ds, which is just the surface area. So our flux is Bz times this cross-sectional area. Well, on the previous slide, we had an expression for our B field, and that was this. So we have this expression for B times S. Finally, we're ready to calculate inductance. Remember our definition. Inductance was flux linkage, although we chose to leave the n explicit here rather than write the lambda, divided by the applied current. Well, we now have an expression for the flux that we can plug in. So let's go ahead and plug in that flux. We see there's two occurrences of n. We also see there's an I naught in the numerator and the denominator, and they cancel. And this is a great check to see if we've done something wrong. The inductance should not be a function of current, assuming we have all linear materials. We could have some exotic materials in here that would change that, but we're not considering that in this course. So all of that simplifies down to mu n squared s over L. And in fact, that is our final answer for the inductance of our solenoid. Now, very often, we're really more interested in the inductance per unit length, because then we can calculate the inductance for any length solenoid. So what we'll do is we'll divide both sides by this L term. When we do that, we get an L squared on the right that we can then bring in with n inside this square operation. So the capital N over L, we interpret this as the turn density. So the inductance per unit length is the permeability times the cross-sectional area times the turn density squared. And so we did it. That was a pretty ugly derivation, but we got the inductance of a solenoid. This is a fun example. A lot of times when we're having fun in the lab, we'll need an inductor that has a certain value. Maybe it's going into a power supply or a filter or something else. It turns out we can wind magnet wire around a McDonald's straw and actually get an inductor that has a pretty accurate value of inductance. And we can use our analysis of a solenoid to come up with an easy design rule that will let us do this. So we need two things. We need a McDonald's straw or a stack of McDonald's straws and magnet wire. So McDonald's straws, these are good because they're relatively tough. We can wind windings around that without deforming the straw too much. And they have a radius of about 3.7 millimeters. Then we need magnet wire. And these come in various gauges. I picked 22 gauge magnet wire for this example. Now, what is the difference between magnet wire and regular wire? Regular wire has very thick insulative coating. It's really meant to be abused and thrown around and all that. Magnet wire is a bit more fragile because the insulating coating is very thin. They're using a thin insulating coating so that you can fit more windings on an inductor. So it's not meant to be abused, and if you do that, you can easily scratch away the insulative coating, and then you'll short circuit your windings, which is not good to do. So that's the difference between magnet wire and regular wire. And so the diameter of a 22 Aug magnet wire with the coating on it is about 0.644 millimeters. So this number will go into the turn density. When we analyze the solenoid, we derive the inductance per unit length. From this, we will derive our design rule of how to turn a McDonald's straw and magnet wire into an inductor with the value of inductance that we need. If we don't put anything in the straw and it just has air, it'll have an air core. So our permeability is really just the permeability of vacuum. The cross-sectional area, if A is the radius of a McDonald's straw, then the cross-sectional area is pi A squared. So we plug this into our formula for the distributed inductance, and we get mu naught times pi, and then all squared A times N over the length of our inductor. Okay. Now, if we wrap our windings tightly so that the windings fall right next to each other with no gaps, our turn density, it turns out, is just 1 over D, where D is the diameter of our magnet wire. Given that, we can replace N over L with just 1 over D. So we're just left with A over D inside of this parenthesis. At this point, we can plug in our numbers. We know the value for the free space permeability. Of course, we know the value of pi. And then we have this ratio A over D squared. Well, A is the radius of the McDonald's straw. D is the diameter of our magnet wire. And when we run the numbers, we get a distributed inductance of 1.3 times 10 to the minus 4 henries per meter. And this really is our design rule, but there's a better way to express that. And that's here. So first we come up with the inductance that we want. And we'll express the inductance in nanohenries. So let's say we want 130 nanohenries. We take that number, divide by 130. That gives us a value of 1. And that tells you how many millimeters long that inductor needs to be. Let's say we wanted an inductance of 260 nanohenries. Divide by 130, that tells us we need a 2 millimeter long inductor. Well, very often we need microhenry sort of inductors, and our inductors end up being, centimeters long, and that's perfectly fine. But that's the design rule that we've come up with, and it was kind of a long path to get there. We had to analyze our solenoid to come up with that expression, and then we looked at the dimensions of mag wire and McDonald's straw to come up with this rule of thumb. Our next example is another sort of big, ugly example. So let's get right into this. What we would like to do is derive an expression for the distributed inductance of a coaxial line. So a coaxial line has an inner conductor, and we have ours with a radius of A. This medium between the two conductors has some permeability, we'll call mu1. And then it has an outer conductor, and the inner radius of the outer conductor is B, and we'll call the permeability on the outside mu2. But we already know there will not be a magnetic field on the outside. So step one, we'll follow the same recipe. Step one is choose a coordinate system. Well, this looks like a cylinder, so let's pick cylindrical coordinates. And we'll let the coaxial cable run in the Z direction. And so then we have rho in the radial direction, and then our angle phi off of the x-axis. Step two, we're going to let this inductor carry a current I. That means there'll be a current I flowing inward for the inner conductor, and then another current I naught flowing outward in the outer conductor. So that was an easy step. We don't have magnetic conductors here. We have electric conductors. That means we actually can have a magnetic field in the inner conductor and the outer conductor. So we'll actually have to calculate the magnetic field in all of these different regions, and we'll do it separately. First, we'll look at the inner conductor, calculate the magnetic field here, then in this region separating the conductors, then in the outer conductor, and then outside of the coaxial region altogether. So we'll call those regions A, B, C, and D. It will turn out, and we'll explain this, but this has high symmetry. We know that the magnetic field will only have a phi component for arguments that we'll make later. But because we have this high symmetry, we can actually calculate the magnetic field much more easily. And we'll get the specifics of the magnetic field using Ampere's circuit law. We'll do a line integral of the magnetic field to get total current. We'll also integrate the current density. And based on this, we'll be able to relate the magnetic field from the current and get an expression for the magnetic field that depends on the current. Now let's talk about why the magnetic field will only have a phi component, because this will really help us and simplify the problem. This really comes from the Biot-Savart law, which we've written here for a volume current. So we have our differential magnetic field due to a differential volume current. And we see that there's a cross product here. And anytime we have a cross product, the answer that we get from that has to be perpendicular to both of those vectors that we took the cross product of. So we have some conclusions. Our current in this case is completely in the z direction, running in the length of the coax. Well, since our magnetic field is calculated from a cross product involving current, it has to be perpendicular to the current. So we conclude that it has no z component from that. The next thing, and we've seen this in previous examples, we know that it won't have a rho component either, because they will end up canceling as we integrate around a circle. So no z component, no rho component, we only have a phi component left. So our total magnetic field we can just write as h sub phi in the phi direction. We still don't know the dependence on rho, phi, and z. We just know that the magnetic field will only have a phi component. In other words, it's going to form loops around the conductors. And from our previous discussions, that shouldn't be very surprising. So we have yet to find this h sub phi and its dependence on rho, phi, and z. A quick note on the current. This is magnetostatic, so we're going to assume that the current is uniformly distributed around the conductor. So this picture on the left is showing that. That's what we're assuming. So we have this evenly distributed current density. I'll just point you to something that's a bit more complicated, but it turns out at high frequencies, this isn't true. We'll have something called the skin effect, and this is something we talk about later. But the skin effect says the bulk of the current is really just at the surface of the conductor. And in fact, in that case, this outer part of the conductor really isn't even contributing to the flow of the current. And the same thing happens on the inner conductor. So we can see right away that the current is not utilizing all of the conductor, and even worse, it's not utilizing all of the conductor evenly, and that makes the math of this much more difficult. But that only happens at high frequencies. At static frequencies or zero frequency, it's uniformly distributed, and so that's what we're going to handle. And I just wanted to point this out, that things deviate a little bit from the result that we'll get when we go to higher frequencies, and this is one of the reasons why. Let's remember exactly how we're going to derive this expression that calculates the magnetic field from the current. We're using Ampere's circuit law, which says there's two ways to calculate a total current. We can integrate the current density, and we can do a line integral of the magnetic field. And so we're going to do both and set them equal to get our expression for magnetic field in terms of the current. So we're looking at a specific line integral path here. And so if we're integrating the current density, we want to integrate the current density that's inside this blue circle, which means we're actually ignoring the current outside of that. So let's derive an expression for the current enclosed in that circle. The first thing we need is the current density that exists throughout that entire inner conductor. And that's easy. It is the total current divided by the total area of the inner conductor. And of course, the current is traveling in the z direction. However, we're only interested in the current that is enclosed within this blue circle here, because that's where we're going to do our line integral. So we'll come up with a ratio here. We have the area enclosed by our rho, that's the radius from the center out to the blue line. So the area enclosed by rho divided by the total area of the inner conductor. So we take this ratio, multiply that by the total current, and that gives us the current enclosed in region A as a function of rho. As rho increases, we're encompassing more and more of that current, so that number will be a function of rho. Well, the area enclosed by rho is pi rho squared. The area of the inner conductor is pi a squared. And so this becomes our ratio that we multiply I naught by. And we can simplify that a little bit. And there's our final expression for the current as a function of rho. The current enclosed by our integration path here. Now on to our second way of calculating the total current enclosed within this blue circle, and that is doing a line integral of the magnetic field. So let's go ahead and write Ampere's circuit law, and here is our function again of the total current in region A enclosed within radius rho, and it's a line integral of h dot dl. Well, we already know the basic configuration of H. It only has a phi component. So let's just write H phi, which we don't know what that is yet. We just know that it's in the phi direction. And then our differential length in cylindrical coordinates is rho d phi, also in the phi direction. So we can bring constants to the outside, which is rho and H phi. Neither of these are a function of phi. And then we're just left with a phi dot a phi, which is 1. And so we just have this integral 0 to 2 pi of d phi. So this entire integral is just 2 pi. So we've derived using Ampere's circuit law the total enclosed current as a function of the magnetic field. Well, we can go back to our previous expression when we integrated the current density to get the total current. That's the current enclosed within a radius rho. And then we also did our line integral and got the total current enclosed within the radius rho. This is now our expression that we can get the magnetic field as a function of the current. And so we solve that equation for H phi, and we can put this in vector form too. So this is the magnetic field intensity in region A as a function of rho. Now we're ready to move on to the next step. The next step is determining the magnetic field in region B. So notice we moved our integration path out into region B. And we'll do this again using Ampere's circuit law. So we have our total enclosed current as a function of rho equals the line integral of the magnetic field. Just like before, our magnetic field is some h phi in the phi direction. We don't yet know h phi, but our differential length in cylindrical coordinates is rho d phi a phi. We'll bring rho and h phi to the outside of the integral because they don't depend on phi, and so we're just left with a phi dot a phi, which is 1. So we're left with our integral 0 to 2 pi of d phi, which is just 2 pi. So we have really the same expression we got on the previous slide. So remember, Ampere's circuit law, there's two ways of calculating total current: integrating current density and doing a line integral of the magnetic field. We did not integrate the current density, and this is easy. this contour is always enclosing just the inner conductor, so the enclosed current is always just I naught. So in fact, that's our next step. I naught equals the expression that we derived up here. So that lets us write an easy expression for H phi. H phi is just I naught over 2 pi rho. So we see that the magnetic field gets a little bit less intense as we move away from the inner conductor. And we can write that in vector form. So this is the magnetic field in region B. And that was easy because we weren't slicing through a current. And now in the next step, when we move to region C, we're back to this problem again where we're slicing through a current, and it'll be a little bit more complicated. So we move into analyzing region C. And you can see we set up an integration path somewhere intermediate in that outer conductor. The first thing we need to do is figure out the current density in the outer conductor. So current density is the total current divided by the area, and we also assign it a direction. So total current, not considering direction, is I naught. But it's in the z direction, and we have a negative sign because the current in the outer conductor is flowing in the negative z direction. So the only thing we have to do then is divide by the area. We want the area of just the outer conductor. So an easy way to do this is to look at the radius of the outside of the outer conductor, calculate that area, the total area, and then subtract the area from the inner radius inward. And that gives us the radius of just the ring. And that's what we're doing up here. So let's go ahead and put in expressions for these. So the total area enclosed by the outer radius of the outer conductor is pi times b plus t squared. And this is the outer radius. And then we subtract the area enclosed by the inner radius, pi b squared. So this denominator, that expression, is the total area of the outer conductor. Well, then we can multiply all this out and simplify a little bit, and we end up with our final expression for the current density in the outer conductor. Given the current density, now we're in a position to calculate the total current enclosed by this contour. And it's a little bit more complicated because we have the current in the inner conductor that's also enclosed, and then we're really subtracting the current in the outer conductor that's within this boundary of our integration and the inner radius of the outer conductor. So how do we do this? So the total current in region C as a function of rho is, first of all, we've enclosed the inner conductor, but then we've only partially enclosed the outer conductor. So we have to do an integration over this area, this ring in the outer conductor that's within our integration path and the inner radius. So we want to integrate all the way around. And we're integrating the current density that we found on the other slide. So we've substituted in our expression for the current density in the outer conductor. Remember, this was negative because the current is flowing in the opposite direction, so I brought the negative sign to the outside. Our differential surface area is simply rho prime, d rho prime, d phi az. That just comes from cylindrical coordinates. And then we're picking our limits of integration. So in terms of rho, we're integrating from the inner radius of the outer conductor out to where we're integrating. So this is rho. So our limits are from b to rho. And then, of course, we want to integrate all the way around the cylinder. So phi goes from 0 to 2 pi. So we've set up our integral, and now we just work through the math of doing this. So I always like to bring as many constants to the outside as possible. So this entire expression is neither a function of rho or phi and can come to the outside. Then we have an az dot az, which just becomes 1, and we're really left with this expression inside the double integral. And then so the first thing I like to do then is isolate this phi integral, which ends up just being 2 pi. So the 2 pi comes to the outside, and now we're just left with an integral over rho prime from b to rho. The reason we're using a rho prime here is because we're using rho out here in the limit. And so it wouldn't make sense to use a d rho and a rho inside here. So we just made it a rho prime. And so all we have to do is integrate rho prime. The antiderivative is just rho prime squared over 2. And then all we have to do is evaluate this expression at the limits and subtract them to get our final expression for the current enclosed within this contour shown in blue. And that is a function of rho. Kind of difficult to obtain, but here we are. We have that expression. And now we're ready to move on to the magnetic field part of this problem. So remember, there's two ways that we're arriving at total current here. What we've just done was integrate the current density. Now we're doing a line integral of the magnetic field around this path. So we've already done this a lot. We have this line integral, h dot dl. We have h phi in the phi direction. We know this from the symmetry. The differential length in cylindrical coordinates is just rho d phi a phi. We can bring rho and h phi to the outside of that integral. And the integral that's left is just equal to 2 pi. And we get 2 pi rho h phi. We keep seeing the same derivation. It hasn't changed. And that will give us the total current enclosed within radius rho. Well, in region C, on the previous slide, we derived this expression by integrating current density, and we can set that equal to the expression that we got by integrating the magnetic field. So we go ahead and do that and set those equal. Then we can solve that for h phi and have our expression for the magnetic field as a function of the current and the radius rho. And so that's what we've done here. Now we move out to region D. And so this becomes simple. Total enclosed current is 0 because we have current I naught traveling one way. Then we have also current I naught traveling the other way, and so they cancel. So the total enclosed current is 0 here. And so when we do our line integral of the magnetic field using the same steps we've done before, so we end up with 2 pi rho h phi, all that just ends up equaling 0 because there's total enclosed current. And so what that tells us is the magnetic field outside of the coax is 0. I know I went quickly, but that's because we did this in a previous example, and it's a rather simple argument. So no magnetic field outside of the coaxial cable. We're almost done. The very last thing to do in step 3 for calculating magnetic field intensity is to bring all of our solutions for the 4 different regions together. And so that's what we've done here in this big ugly expression. And then I visualize it over to the right. So this top diagram, I'm showing the coaxial cable, and then I've overlaid the amplitude of the magnetic field as a function of position. So we're working out in radius and plotting this magnetic field. So what we can see is the magnetic field in the inner conductor increases rather sharply linearly and ends up being a maximum right at the outside of that inner conductor. Then in the region between the conductors, it decays as 1 over rho. Then in the outer conductor, it also decays approximately 1 over rho. However, there's a rho mixed in here which changes that a little bit, but it still decays basically as 1 over rho. And then it is 0 outside the coaxial cable. So if we were to go ahead and actually visualize this and follow the right-hand rule, on the inner conductor we have the current going inward into the screen. So that means the magnetic field would be circulating in a clockwise direction. And we can look at the thickness of these arrows to convey the intensity of the magnetic field. So it increases rather sharply and linearly, and then it decreases to 1 over rho, and then it decreases again, sort of a modified 1 over rho, and then is 0 on the outside. So I think this is a pretty good visualization that conveys both the amplitude and the direction of the magnetic field in the cross-section of a coaxial cable. So that's the end of step 3 and the big ugly step. It's just smaller steps from this point forward. When we analyzed our solenoid, our next step was to calculate the magnetic flux density B from the magnetic field intensity H, and we used the constitutive relation to do that. Then we integrated the B field to get the flux, and then we used that to calculate the inductance of the solenoid. Now we're going to take the alternate approach to demonstrate that. Given H, we can calculate the total magnetic energy and then use that to calculate the inductance. So we have found the field in our 4 different regions. So if we're calculating the total magnetic energy, we can apply that integral to each of those regions separately. So that's what we'll do. Well, we know that the magnetic field outside of the coaxial cable is 0, so that last integral drops out. Another thing, typically in a coaxial line, this outer conductor is very thin. And we already know by the time the magnetic field reaches the outer conductor, it's already pretty small. And so if that outer conductor is rather thin, it also becomes negligible compared to the other terms. So in fact, we really only have to proceed with these first 2 terms to calculate a pretty good estimate of the total magnetic energy. So here we are, total magnetic energy. We have to evaluate this integral in both regions A and B. C and D have dropped off. So let's look at this first integral in region A. So what we can do is we can plug in our expression that we found for H, which is in region A. Our differential volume in cylindrical coordinates is rho, d rho, d phi, dz. And then we need to pick our limits of integration. Well, we're integrating in the inner conductor. We're going from 0 to A in the rho direction, so 0 to A. We're going all the way around in the phi direction, so from 0 to 2 pi. And then we're integrating over the entire length of the coax from 0 to L. So at this point, it just becomes a math problem. I like to bring as many constants to the outside as possible, and all we're left with is really a rho cubed inside. That lets us isolate our phi integral and our z integral, and we can see that this will just be L, and this one will just be 2 pi. So in fact, that's what we get. Let's continue. The next thing would be to bring this 2 pi L to the outside of the integral. And now we're just left with integrating rho cubed. So the integral of rho cubed is rho to the 4th divided by 4. And so we'll evaluate that at the limits and then subtract. And then we can simplify that. And we have our final expression for the magnetic energy in the inner conductor. Now we're ready to move on to the outer conductor, which is a very similar derivation. So on to the second term. Now we're integrating from A to B, just in this space between the inner and outer conductor. Well, we have the expression we got for the magnetic field in that space between conductors. And our differential volume in cylindrical coordinates is still rho, d phi, dz. And then the limits of integration. The only limit that has changed is our limit in the rho direction. Because in the previous, on the inner conductor, we're integrating from 0 to A. But now we're integrating from A to B. So A to B. So really the only 2 things that have changed are the limits on the rho integration and our expression for the magnetic field, which is actually a little bit simpler in this case. So we bring a bunch of constants to the outside. We isolate the phi and z integrals. And we know that the phi integral is 2 pi and the z integral will be L. So let's keep going. We can bring the 2 pi L to the outside of the integral. And we're just left having to integrate 1 over rho. Well, the antiderivative of 1 over rho is the natural log of rho. And so we'll evaluate that natural log at the limits and subtract. And we can combine those and just call it natural log of B over A. So that is the magnetic energy in the region between the inner and outer conductor. Pulling these together, the total magnetic energy is the magnetic energy in region A plus the magnetic energy in region B. So we add these together, we see a bunch of common terms, and we can pull them to the outside, and we have a nice expression for the total magnetic energy. We are finally ready to calculate the inductance. So the inductance is 2 times the total magnetic energy divided by current squared. So we plug in this big ugly expression we had for the total magnetic energy, which had an I squared in here. And of course, we're dividing by I squared, and that's great. The current term has canceled. Inductance can't be a function of current, assuming we're having linear materials in this. And so that's a great check that we haven't goofed somewhere. So we have our final expression for the inductance of a coaxial line. And like we did before, usually it's more useful to have an inductance per unit length so that we can figure out the inductance for any length coax line. So we bring this L over to the left side of the equation, and we have the inductance per unit length. Now let's apply this to a realistic case, an RG59 coaxial transmission line. So this is the coaxial cable that screws into the back of older televisions. I understand everything's HDMI now, but in the old days we had these coaxial transmission lines, and you'll still see them around. So it turns out, if you take what we did in electrostatics when we derived the distributed capacitance, and you take what we've just done by deriving the distributed inductance, we've actually done a rather sophisticated analysis of a coaxial line. So if you'll recall from electrostatics, we derived that distributed capacitance. We just finished describing the distributed inductance. Now this lets us do something pretty neat, and I'm jumping ahead in topics, which is really reserved for transmission lines. But we're in a position now to calculate the characteristic impedance of the transmission line. And the characteristic impedance is the square root of the distributed inductance divided by the distributed capacitance. So we can do that now. So the RG59 coax that we're showing to the right over here has these following parameters. The inner conductor diameter is about 0.81 millimeters. It's a 20 Aug wire. The outer conductor diameter, 3.66 millimeters. The dielectric, the white stuff here, is normally Teflon, which has a dielectric constant of 2.1. And the data sheets usually specify a distributed capacitance of around 86.9 picofarads per meter. And they don't specify a distributed inductance for some reason. So if we use our expression for distributed capacitance and throw in the numbers we have, we get 77.46 picofarads per meter. That's a little bit lower than the specified capacitance, but we made some approximations to get there. We then throw in the numbers to get the distributed inductance, and we arrive at 352 nanohenries per meter. Now what we can do is combine those. The square root of distributed inductance over distributed capacitance gives us the impedance, and we get 64.7 ohms, so 65 ohms. Well, the actual specified impedance of this line is 75 ohms. So you can get a feel for how far off these calculations are, but we're definitely close. We're definitely within an order of magnitude, and it gives us a great feel about how all these different parameters affect distributed capacitance, distributed inductance, and ultimately the impedance. And the impedance is something that we'll talk about in depth when we get to transmission lines. And it's not even so much that the impedance value is that important. What is important is that when the impedance changes, we'll get reflections and scattering in transmission lines. Normally we don't want that because we're losing signals, but sometimes we do because that helps us make things like filters and other types of circuit elements. So that concludes this lecture. I hope it was helpful.